Dear students, welcome to the second lecture on design of flywheel. In the previous section, we had seen the various types of flywheel, their construction methods, and we had seen in detail the stresses induced in solid disc flywheel. Now, before moving to the numerical section on solid disc flywheel, I would like to introduce you some of the pages from design data book given by V.B. Bhandari. Let us see the pages. The very first page of the flywheel, that is chapter number 25 from the data book. The table number 25.1 gives us the coefficient of fluctuation of speed. Now, coefficient of fluctuation of speed Cs can be computed as omega max minus omega mean upon omega, and this omega is nothing but equal to omega max plus omega mean upon 2, that is the mean angular velocity. This section we had seen in detail in this previous section, and so let us move to the next part. The second part of this table gives us the coefficient of steadiness of the flywheel, where coefficient of steadiness m is reciprocal to the coefficient of fluctuation of speed. Therefore, m is equal to 1 by Cs, where we can see that if Cs increases, m decreases. So, as the coefficient of fluctuation of speed increases, steadiness of the flywheel decreases. The table number 2 in the chapter 25 gives us the coefficient of fluctuation of speed for various machineries. Now, this table gives us the values of Cs for various machine equipments like crushing machinery, generators, gear drives, hammering machines, machine tools, shearing machines, spinning machine, textile machinery, particularly reciprocating pumps and compressors. So these are some of the common machines where we come across the application of flywheel. So whenever we will need to design flywheel for such applications, we can use this data, the coefficient of fluctuation of speed, to further compute the dimension of flywheel. Here we can see that for particularly hammering machineries and crushing machineries, coefficient of fluctuation of speed is very high, and for rest of the machines, the coefficient of fluctuation of speed is low. The third table in the data book provides us the coefficient of fluctuation of speed for engines. So when the engine is used at agriculture equipment, the coefficient of fluctuation of speed is 0.05. When it is used in workshop machineries, it is 0.30. When it is used in weaving and spinning machineries, it ranges from 0.01 to 0.02. When engine is used in DC generators, it is 0.006. So this data will be useful in future. Table number 25.4 also provides us the coefficient of fluctuation of energy. The fundamental formula for coefficient of fluctuation of energy, where we can see it is the ratio of the maximum fluctuation of energy to the work cycle. This part is also discussed in the previous section of this flywheel. Table number 25.5 provides us the coefficient of fluctuation of energy, the values of coefficient of fluctuation of energy for various types of engines. So when the engine here, in the first column, it is provided that the various types of engines, the number of cylinders in the engine, and its working cycle, whether it is 4-stroke cycle or 2-stroke cycle, and accordingly the coefficient of fluctuation of energy is given to us. So we can see in single acting and here in double acting engines, the fluctuation of energy is quite high in case of 4-stroke engine. So this data might be useful in future, but as far as our syllabus is concerned, we may not come across this table. Mass density of the material is provided in the table number 25.6, and this is very much important. That is the must, but in many problems directly the values of density of material are provided. The next table is very important, which gives us the formula for mass moment of inertia in terms of maximum kinetic energy fluctuation. So the difference of maximum kinetic energy U naught plays crucial role, and this actually defines the need of the mass moment of inertia of flywheel. So once we find U naught, we can find the value of I which is desirable for the particular application, and here omega is nothing but the mean angular velocity of flywheel. Now next table gives us the data for solid disk flywheel, where figure is provided. This is T is the thickness, capital R is the maximum radius of the disk, and types of stresses are shown in the figure, that is sigma R and sigma T. The moment of inertia R in terms of R and M is given to us as mr square by 2, and if we are knowing the value of omega, the density of material and the thickness, then the mass moment of inertia of the flywheel in terms of R, T and rho is given to us in this table. The next part of the table provides us the equations for finding out the maximum tangential stresses and radial stresses at any radius r when it is moving from 0 to r. So now r can be any value ranging from 0 to capital R. So at any distance r, we can find the value of sigma r and sigma t by means of this formula. And as far as equation is concerned, we can see that if r increases, the value of r upon r decreases. The value of r upon r increases, and as this value increases, the value of maximum stress, that is tangential stress or radial stress, decreases. So we can say that at r equal to r, the stress is minimum or 0, and when it is maximum at when r becomes 0. So the maximum amount of stress, that is tangential stress or radial stress, can be computed by this formula when r becomes 0. Now in this problem number 1, we have been given that a machine is driven by a motor which exerts a constant torque. The resisting torque of the machine increases uniformly from 500 Newton meter to 1500 Newton meter through a 360-degree rotation of driving shaft, and drops suddenly to 500 Newton meter again at the beginning of the next revolution. The mean angular velocity of the machine is 30 radian per second, and the coefficient of speed fluctuation is 0.2. A solid circular steel disc of 25 mm thickness is used as flywheel. The mass density of the steel is 7800 kg per meter cube, while the Poisson's ratio is 0.3. It is desired to calculate the outer radius of the flywheel and the maximum stresses induced in it. So as far as given data is concerned, angular velocity is given to us as 30 radian per second. The coefficient of fluctuation of speed is given to us as 0.2. The thickness of the flywheel is given to us as 25 mm. Poisson's ratio mu is given to us as 0.3, and density of the material used for flywheel is 7800 kg per meter cube. Now, looking to the application, it is given that the motor provides a constant uniform torque. So we will be receiving constant torque from the motor, but the machine system have the variable torque, so driving torque requirements. So during the cycle, the torque increases uniformly from 500 Newton meter to 1500 Newton meter through a cycle of 360 degrees. So, and it suddenly drops to 500 Newton meter again at the beginning of the next cycle. So therefore, we have drawn the theta diagram as per the given condition when the torque is increasing from 500 Newton meter to 1500 Newton meter during the cycle of 360 degrees, that is 2 pi. Now we have to compute the dimensions of the flywheel. So before computing the dimensions of the flywheel, we have to compute the mean torque supplied by the flywheel. So mean torque is nothing but the torque which is provided throughout the cycle. So mean torque is equal to the area under OABG, that is the work done per cycle. So during one cycle, the work done can be computed as the area under AB in T theta diagram. So upon the time of the cycle. So it is nothing but area OABG upon the length OG, that is equal to, now OABG, area OABG can be computed as the 500 plus 1500 by 2 into 2 pi. So area can be determined by this formula. We can again determine the area by dividing this OABG in two parts as OA, say this point X, and G, this becomes a rectangle, plus the area AXB. So this triangle, separately we can find out the area for triangle and rectangle and add them, then also we will get the same area. So putting the area here and the length 2 pi gets cancelled, and we get the mean torque as 1000 Newton meter. Now when we see the cycle of the machine system, here the torque is varying from 500 to 1500 uniformly. Now let us say Tm is the mean torque and it is at the mid, that is 1000 Newton meter. So when the driving torque is at the point A, at this point A, the driving torque is lesser than the torque supplied by the flywheel. So we can say that this torque is not just supplied by flywheel, it is supplied by the machine, that is motor and flywheel itself. The total torque is supplied by both the systems. So the power supplied by the motor during this phase will be utilized to increase the speed of the flywheel. Now from point A onward, when it moves to point E, the speed of the flywheel will go on increasing because the driving torque is smaller than the mean torque. And as it reaches to E, the flywheel attains the maximum angular velocity. The point E onward, the speed of flywheel decreases because the driving torque or load torque is greater than the mean torque, and now the speed decreases and it goes on decreasing up to point B. So the flywheel will record the lowest speed at point B, and suddenly the torque will reduce to 500 Newton, and then the cycle will repeat. So we can say that the system will have maximum velocity at point E and the minimum velocity at point B. So the maximum fluctuation of energy U naught can be measured as the area of the triangle EFB. Now to compute the area of the triangle, we can say that area of the triangle is equal to half into base, that is half BF into half base into height, that is half of the base into height, that is EF into BF, half of EF into BF. So EF is nothing but equal to 2 pi minus pi, and BF is nothing but equal to 1500 minus Tm, that is 1000. So we get U naught, that is the fluctuation of energy during the cycle, equal to 250 pi. Now we are interested to find the required dimension of the flywheel. Now this is the maximum fluctuation of energy which is required. So the mass moment of inertia required for the flywheel is U naught upon omega square Cs. Now this formula is already discussed in previous section, and we can see this in the data book again. So if we go to the data book here, we can see the moment of inertia of the flywheel in terms of U naught. So this formula where omega is the mean angular velocity of the flywheel. Now coming to the previous section, here we can see that I is equal to U naught upon omega square Cs. Omega is directly given to us as 30 radian per second. So putting the value of omega as 30 radian per second into coefficient of fluctuation of speed, that is 0.2, and U naught as 250 pi, we will get directly the value of moment of inertia required from the flywheel for the given machine system. So this comes to us as 4.3633 kg meter square. Now to have this amount of moment of inertia, we have to design the flywheel. So now we know that the moment of inertia, mass moment of inertia of flywheel for solid disc flywheel, I is equal to pi by 2 rho T R square. Now this formula is again given in the data book. So coming to the data book again, in solid disc flywheel, it is been given to us this formula I equal to pi by 2 in the table 25.8 and the equation 25.11. So using this formula we can have the moment of inertia. We can find the radius of flywheel if we fix the value of density and the thickness. So already it is given that thickness of the flywheel is 25 mm and density of the material is 27800 kg per meter cube for steel. So we can say that the R which is required to generate this much amount of mass moment of inertia, required radius of the flywheel is 350 mm. Now coming to the third part, which is the stress induced in the flywheel. So again we go to the data book. Now stress induced in the flywheel is given in the table 25.8 and Here this is the value of sigma t and sigma r, that is the tangential stress and radial stress in the disk at any radius r, when capital R is the maximum radius of the flywheel. Therefore, but we are interested to find maximum stresses. Therefore, maximum stress, that is tangential stress or radial stress, is equal to rho v square by into by 10 to the power 6 into mu plus 3 upon 8, where mu is the Poisson's ratio, and this value occurs maximum when R is the resisting torque of the machine is constant throughout. The maximum stress occurs when at R equal to 0, and this value can be computed by putting the value of rho v and Poisson's ratio mu. Now mu is given to us as 0.3. The peripheral velocity v can be computed as omega into r. So already we have value of r, so putting this value of r in this equation, we get the v. Now as far as given data is peripheral velocity, density is already known, and putting these values in the equation, we will get the maximum radial or tangential stress in the flywheel equal to 0.35 Newton. Thickness of the plate is 50 mm and the density of the material is 7. So here we complete the problem. Now looking into number 1. Let's move to the problem number 2. The equation consists of fluctuating terms sin 2 theta and cos 2 theta. So as it have the same crank angle and sin theta and cos 2 theta, cos sin 2 theta, cos 2 theta, it will have the same curve at the upper and lower, that is ups and downs will be same, and that's why it will have a zero mean. Hence we can say that the equation gives us a curve which have same ups and downs. Because of this, we can say that mean torque developed in this equation is nothing but equal to 14,250. Now therefore Tm is equal to 14,250. Now when the value of torque, that is driving torque, now we can see here the driving torque is increasing and it reaches to the maximum level, then it goes down and it goes to the maximum minimum level, and again it increases. So when the mean torque becomes equal to the driving torque, so in that case here the mean torque will come across the driving torque. At this case T will be equal to Tm. Therefore when T equal to Tm, this value of the equation has to become 0. So putting the value of this, that is 2200 sin 2 theta minus 1800 cos 2 theta equal to 0, we get theta, that is 2 theta equal to 29.29 degrees, or plus 180 if we do, then it is around 220. And if we find the value of theta, then the theta comes to us as 19.645 degree, and r, the second value of theta, goes to 109.645. The third value can also again be computed as adding the 180 degree. Here we can see we will get the third position where the value of T will become Tm. So if we see these two values A and B, where the torque is going to increase, driving torque is going to increase in this period where the value of torque is greater than the mean torque provided by the motor. Therefore this is in this area there will be the fluctuation of energy. The energy will go down, and this is the amount where we need this amount of energy has to be taken care by flywheel. So here angle at theta equal to 19.65 and at theta equal to 109.645, the value of torque becomes Tm equal to Tm. So the diagram shows here the maximum peaks and where the position of maximum and minimum angular velocities. Now at point A, as we had seen in previous problem also, the velocity of the flywheel will go on increasing, and at point A it will be the highest, and when it will move towards B, the velocity will go on decreasing and it will record the lowest velocity at point B. Therefore, uh, the maximum fluctuation of energy will be in between A to B when flywheel moves from cycle A to B. Therefore, we can integrate the equation the T minus Tm into d theta, integration of T minus Tm into d theta from when point moves when the cycle moves in between A and B. So putting the value of the theta and integrating this equation T minus Tm. Now if this is the value of Tm, therefore T minus Tm is nothing but equal to 2200 sine 2 theta minus 1800 cos 2 theta. Therefore putting this value of as T minus Tm and integrating this equation with respect to theta, we get the answer for maximum fluctuation of energy that will occur during the period of the cycle AB, and it comes to us as 2842.2 Newton meter. Now moving to the second part of this problem, we need to find the diameter of flywheel disc. Now already we know from the data book that I is equal to u naught upon omega square Cs, where omega is the angular velocity of flywheel which is attached to the engine. So already RPM is given, so we can compute the value of omega. We know the value of u naught and we also know the value of Cs. So here we get the required desirable amount of moment of inertia for this application. Now equating this value, and from the table we have for solid disc flywheel we have I in terms of R, rho and T, and putting the value in that equation. Now already rho is known, thickness is fixed to 50 mm, and converting 50 mm into meter, so it is 50 by 1000, and here we can find the value of R, and R comes to us as 1175 mm. Now if we look at this figure, there is no need actually to find the ups and downs position, but if we desire to find these values, then already mean torque is known. At theta equal to 0, if we compute, we will get in from this equation T equal to 22,450, and when at the mid position of AB, definitely there will be the highest peak of the torque, and at the mean position the degree comes to us as 64.645. So putting the value of theta equal to 64.65 in this equation, we will get torque equal to 17,093. And similarly, in the similar fraction, we will get, adding this by 90 degree by pi, we get the next position, that is the lowest position of the torque, and that angle will be 154, and putting this value of theta in the same equation we will get the value of the minimum torque which is occurring in the cycle, and that comes to 11407. So here we had find the diameter radius of the flywheel, where that can from which we can compute the diameter of the flywheel which is required to generate this much amount of moment of inertia. So thank you very much.